Swayam Prabha. Digital India. Educated India.
Welcome to the first lesson of module 5, which is on bending of beams part 1. In fact, in the last few modules, or the 4 modules which we have looked into, they are on the effect of the axial force on bars, and correspondingly we have looked into the aspects of stresses and strains. Subsequently, we have looked into the effect of twisting moment on bar. Now, in this particular lesson, we are going to look into some other aspects of loading on this kind of system. So, it is expected that once this particular lesson is completed, one should be able to understand the concept of beam. In fact, we will define the term what is meant by beam. So long we were talking about the forces in a bar. Now, we have brought in a specific term which is called beam. We will look into what is meant by that, and different forces which act on beam. Then one should be able to understand different types of supports and types of beams. One should be able to understand the concept of shear force and bending moment, and also one should be in a position to evaluate reactive forces for different kinds of loading on different types of beams. Hence, the scope of this particular lesson includes the definition of beam, the different types of supports and types of beams. In fact, we will look into that what a beam means and what are the different types of supports on which a beam member is supported, and the different types of loading that the member will be subjected to. One should be, and then the scope is included as the evaluation of reactive forces in different types of beams, then concept of shear force and bending moment in beams, and the examples for evaluation of reactive forces for different beams under different loading conditions. We will evaluate the reactive forces in beam members, and consequently we will look into how to evaluate the shear force and the bending moment. Well, let us look into the answers of the questions which was posed last time. Now, the first question posed was how the strength to weight ratio of a bar subjected to torsion is defined. Now, in fact, the previous lesson was the last lesson of module 4, which was on torsion. Now, so the questions which were set were related to the torsional aspects. So, before we go to the bending of beams or bars, let us first look into the aspects or the answers to the questions which were given last time. Now, how the strength to weight ratio of a bar subjected to torsion is defined. Now, if you remember, we did an example wherein we had evaluated the strength to weight ratio. Now, basically by the term the strength of a bar against twisting motion, we mean that how strong the bar is to resist the twisting moment. So, its carrying capacity, the carrying capacity of the bar of the twisting moment is basically its strength, and weight, as you know, the weight of the bar, its cross sectional area multiplied by length times the unit weight of the material gives the weight. So, the ratio of these two parameters will give us the strength to weight ratio. So, the strength to weight ratio of a bar is defined as the capacity of carrying twisting moment to the weight of the bar. Now, if twisting moment is defined as T or designated as T and weight is designated as W, then the ratio of the strength to weight is T by W, where W is the weight given by the cross sectional area multiplied by length multiplied by the unit weight. So, T divided by this ratio gives us the strength to weight ratio. A is the cross sectional area, L is the length of the member, and gamma is the unit weight of the material. So, this is what we define as the strength to weight ratio. Now, the second question is the what is the torsion equation. Now, after going through the module on torsion, now you know that the torsion equation is defined by this expression, where this is given as T by J is equals to tau by rho is equals to g theta by L. Now, T here is the twisting moment or the torsional moment which is acting on the shaft, J is the polar moment of inertia, and as you have seen that for solid section polar moment of inertia is pi d4 by 32, where d is the diameter of the bar, and for tubular section this becomes pi by 32 times d outer to the power 4 minus d inner to the power 4. So, for solid section this is the polar moment of inertia, and for tubular section this is the polar moment of inertia. Tau is the shear stress, rho is the radius at the point where we are trying to define the shear stress, g is the shear modulus, g is called as shear modulus, and theta is the rotation of the bar, and L is the length. So, these are the terms, and this is what is defined as the torsion equation, which is T by J is equals to tau by rho is equals to g theta by L, and this we where all the terms have their usual meanings, this is what we have defined in the module. Now, the third question is that what is the value of maximum normal stress in a solid circular shaft subjected to a twisting moment. Now, this also we have discussed through a problem. Now, let us look into this once again, that if this particular bar which is fixed at this end subjected to a twisting moment T, which is a positive moment, as we have defined that when the twisting moment is acting in the bar in such a way that the thumb is projecting towards the positive x direction, that is the positive twisting moment. So, when it is subjected to the positive twisting moment, then if we look into a small element, that what are the kinds of stresses that is acting. Now, this particular element is subjected to shearing stress, which is in this form. Now, if we try to plot this shearing stress of this element in terms of a Mohr circle, now this is the sigma axis of the Mohr circle, this is the shearing stress axis of the Mohr circle, and these are the positive directions for tau and sigma. Now, here as we have designated earlier, the shearing stress which is acting on this particular element, according to our convention this is negative, as this is this particular shear along with this complementary shear is making a moment in the clockwise direction, which is negative. So, here on this particular axis it is representing this particular point, whereas the shear on the other plane it is positive, which is making a clockwise moment. So, this is represented by this particular point. Now, if we plot the circle, then this is the Mohr circle of the stress, and this particular point which is on the Mohr circle represents the plane where we have the maximum normal stress. This we call as sigma 1, and incidentally the value of which is equals to tau. If tau is the shearing stress, this is tau, and this is also tau, which is the radius of the circle, and since normal stress is 0 on this, which is a state of pure shear. So, the normal stress is equals to tau. Now, this particular point is at an angle of 90 degree with reference to the reference plane, which is this. So, in the physical plane it will, if we move clockwise 45 degree, since here it is in the Mohr's plane 2 theta is 90 degree, theta is 45 degree. So, if we move clockwise by 45 degree, which is shown here, now perpendicular to this the plane which we get is the plane along which it will fail, and the direction of the normal stress sigma 1 is this. So, this is what is the normal stress sigma 1, and consequently the other stress, normal stress, which is a minimum value, will be sigma 2, which is equals to minus tau. So, these are the values of the normal stresses which are getting generated because of the action of twisting moment acting in a bar. Well, now let us look into the aspects with which we are going to deal today. Now, so long we have discussed about the forces which are acting in a bar, which is acting in the direction of its long axis, and thereby the load which is acting, we have called that axial load or axial force. Now, at any cross section, if we try to find out the stress corresponding to that, we have looked into the normal stress as equals to the load divided by the area. Also, subsequently we have seen that a bar, when it is subjected to a twisting moment, the vectorial notation of this particular twisting moment is in the direction of the axis, which is the long axis of the bar. Now, we are going to discuss about the loading in a bar, where the vectorial directions of this loading, either the direct load or the moment, is perpendicular to the axis of the bar, and that is what, and these particular kinds of loads are the transverse to the bar, and we call those kinds of members which are subjected to these transverse loads are the beams. Now, in case of bars, the loads were axial and their vectorial direction is along the axis of the bar, whereas for the members which we are terming as beam, there the loads are transverse to the member, and the vectorial direction of these forces, either the loads directly or the moment, vectorial direction of the moment, they are perpendicular to the axis of the bar. Now, let us look into, supposing if we have a bar in which the loads which are acting are transverse to its direction. So, the vectorial direction is perpendicular to the axis of the bar. Also, if we have a moment which is acting in the beam, now this particular moment, if we look into this is the beam, you have a moment in its plane. So, the normal to it, so the vectorial direction is perpendicular to the axis of the beam. So, this kind of loading acts on a bar, and this we designate as beam. So, members which are subjected to loads which are transverse to the axis, the longitudinal axis, are termed as the beam, and the members are subjected to forces or moments, either they are subjected to the forces or the moments having their vectors perpendicular to the axis of the bar. Now, when all these forces which are acting in the beam member, which are transverse to this particular member, they are acting in the same plane. Now, this is the plane of the beam, and the forces which are acting on it along with the moment, they are in the same plane, and that is why we term these kind of structures as the planar structures. In the same plane we have the bar and the loading, and consequently we look into when these bars or the beam will be subjected to these transverse loads, it will undergo deformation, and this deformation also will be in this particular plane. As we will go along, we will subsequently look into the deformation aspect of it, and when this load, the forces which are acting on this beam along with the plane of the beam and its deformation are in the same plane, we call them as a planar structure. Also, if we in fact in the previous lesson you have seen that when we were talking about the moment which is about an axis which is perpendicular to the cross section. Now, we are going to discuss about the moments which will be about the axis which are in the plane of the cross sections. So, if we look into the cross section of this, say for example, if the cross section is a rectangular one, then the axes which lie in this particular plane, the bending or the moment will be acting about these axes. Now, when this moment acts about the axis, say for example about this axis, it lies in the plane of this beam itself. And also, if we look into both the moments, the vectorial direction of both the moments are perpendicular to the long axis of the beam. Now, when we are dealing with the bending moment which are in the plane of the beam along with the forces, we call that plane as the plane of bending. And since because of this particular moment, the beam member or the member which is subjected to the transverse loading undergoing a bending we call these moments as the bending moments, as we will look into gradually as we go along. Now, before we really go into the details of beams, let us look into some kind of supporting arrangement on which a bar is supported. Now, one of such supports we call as a pin support or hinge support. Now, let us look into what we mean by that. Now, here you see diagrammatically we have shown some figures. Now, this is the part of a beam. Now, this is supported by a joint in which this particular end of the beam cannot undergo displacement in the horizontal direction, cannot undergo displacement in the vertical direction, but this pin allows the bar to move in this form. That means, it can undergo a rotation, it cannot move horizontally, it cannot move vertically, but it can rotate. So, the rotation of this particular end of the bar is allowed. So, it can have some amount of rotation which we may designate as theta. Now, if we generally when we look into the problems, we designate them in this particular form, or we diagrammatically we show in this particular form that this particular type of support indicates that it is hinge support or pin support. Also, now if we have a support of this particular form wherein it is resting on two rollers. Now, when this part of the segment will be loaded, what will happen is this particular support can move. This can move in the horizontal direction. Since it is supported on the roller, hence the horizontal movement is possible, but the movement in the vertical direction is restricted. Also, it can have rotation as we had in the previous case for a hinge support. Now, when we talk about so this kind of support we generally call it as the roller support. Now, in these two kinds of supports, both in the hinge support and the roller support, as you can see, in case of hinge support, the movement of this particular end both in the horizontal direction and the vertical direction is restricted. Hence, since they are restricted, so it is expected that some amount of reactive forces will be generated, and these reactive forces will be in the vertical direction and in the horizontal direction. Now, in case of roller support, since restriction of movement is only in the vertical direction and it is free to move in the horizontal direction, so there will be a vertical reactive force which is perpendicular to this roller plane. Now, this is a kind of a support which we call as fixed support. Now, this particular end is fixed, this particular end of the beam is fixed at this point. Now, the meaning of this fixity is that this particular point cannot have any displacement in the horizontal direction, cannot have any displacement in the vertical direction. Also, this particular part is not allowed to rotate freely. That means, this particular axis if we look into, it will have something like this. That means, it will remain straight over here. So, no rotation as we had in this case or in this case is allowed in this case. So, here it is both the horizontal movement, the vertical movement as well as the rotational movement are restricted. Now, when these three motions are restricted, naturally corresponding to all these three motions we will have the reactive forces. Since the vertical motion is constrained, so there will be a vertical reaction. Since the horizontal movement is constrained, so there will be horizontal reaction, and since the rotation also is constrained, earlier it was allowed to rotate, now since it is not allowed to rotate, it has to be held back. So, there will be a couple or a moment that will be acting at the support. So, hinge support is having two reactive forces, one vertical and one horizontal, because it is not allowed to move in these two directions. In case of a roller support, since it is allowed to move in one horizontal direction, there will be a vertical support only or vertical reactive force only, and for a fixed support we will have three reactive forces. They are the vertical reactive force, the horizontal reactive force and a moment at that particular point. So, these are the different kinds of supporting arrangements that we have. So, these are the three supports which have been shown over here, or it is written that pin support or hinge support, the roller support and the fixed support. Now, based on these kinds of supports, we classify the beams as well. Now, when a member or a beam member is supported at its two ends, now since it will be subjected to the loading, they are supported. Now, say on one end it is supported by a hinge connection, on the other end it is supported by a roller connection, roller support, and when they are subjected to the transverse loads, it resists transverse load by generating the reactive forces in the supports. Say the reactive forces generated in these supports will be of this particular form, and this kind of beam we call as simply supported beam. So, when we talk about simply supported beam, it means that one end of it is hinged, the other end is on roller. Now, if you notice over here that we have two unknown reactive forces on this particular end A, on this particular end B we have one reactive force. So, there are three unknown reactive forces, and as we know that the equations of static equilibrium, we have three equations. So, we can solve these three unknown reactive forces using three equilibrium equations. So, these kind of members are called as statically determinate, because the three unknown reactive forces can be readily determined using the three equations of statics. Now, we encounter another kind of beam which we call as cantilever beam, where the beam member is fixed at one end and it is free at the other. So, this kind of beam member is called as cantilever beam. Now, here when this is subjected to load, at this support, as we have seen in the fixed support, it is expected that there will be three reactive forces generated. One is the vertical force, one is the horizontal force, and another one is the moment. So, these three reactive forces will be generated at this support, and again if we look into this particular member, since we have three reactive forces, these three reactive forces can be evaluated using equations of statics, and hence again this member also is a statically determinate member. Now, sometimes we use a beam member which may not be any of this category, but could be combinations of these. Say for example, if we have a beam which is hinged at this place and say placed on a roller at this particular place and subjected to some kind of loading on the transverse plane. Now, here this part of the beam is extended beyond the support, or this part of the beam is extended beyond the support point. Now, these parts we generally call as overhang. This is the overhang part of the beam. Now, this is a simply supported beam with overhang. Now, this part is something like a cantilever beam, but in this cantilever beam here the rotation is allowed, because it is supported with a roller support at this point, has a vertical constraint, but then it is because of this overhang it is expected that it can generate moment, but and also it can generate rotation, but being a roller support that cannot resist any rotational aspect over there. So, there is expected to be rotation. Now, this kind of beam member we generally call as beam with overhang. So, these are the different kinds of designations, either simply supported beam or cantilever beam or beam with overhang. So, henceforth whenever we mean that a simply supported beam is loaded with transverse load, it means that the beam is supported on a hinge support at one end and the roller support at the other, or if we say that a cantilever beam is loaded with such and such loading, it means that the one end of the beam is on a fixed support and other end is free, and when there is a fixed support it is expected that there will be three unknown reactive forces which are to be evaluated using equations of statics. Well, having looked into then the types of supports and the types of beams we designate, let us look into the different types of loads that a beam member encounters. Supposing we have a beam let us say it is a simply supported beam which is hinged at one end and supported on roller at the other. Then we have designated one load which is known as concentrated load. Now, the meaning of this is that if a load which acts on a very small area, infinitesimally small area, which is distributed in that particular small area, then that force or the load we call as a concentrated load, which is acting on a very small area. So, this kind of loading we call as the concentrated load. Many times we encounter that, say, the whole of the beam may be subjected to a load which is distributed over the entire length. This is the length of the beam, and the entire length of the beam is subjected to a load which is uniform, and the intensity of this load could be, say, Q per unit length. Now, this load is called as the uniformly distributed load, as it is distributed over the entire span having uniform intensity. So, this kind of loading system we call as uniformly distributed load, or in short many times it is said as UDL. So, the beam, a simply supported beam, is subjected to an UDL. It indicates that a beam which is hinged at one end and on roller support on the other is subjected to uniformly distributed load over the entire span of the beam or the length of the beam. Now, there is another kind of loading which we call as linearly varying loading. Now, the meaning of linearly varying loading is, say for example, if we have a beam member or a simply supported beam which is hinged at one end and the on roller support on the other, and this has a load which is varying in this form in a triangular pattern. Now, here the intensity is 0 and here to a say maximum intensity Q. So, this span of the beam or the length of the beam over in its entire length is subjected to a load which is linearly varying. Now, it can be of different types. It could be in the form of this as it is indicated over here, or we could have a loading which is say it is varying in this form, or we can have the loading on the member which is varying in a trapezoidal form. So, there could be different kinds of variations. Say here we have intensity Q1, on this we have intensity Q2, and between these two it is varying in this form which is a trapezoidal variation, but between these 2 points, since Q1 is constant over here, again from here to here it is linearly varying. So, everywhere the intensity of the loading which is varying is in a linear form. So, everywhere it is varying linearly. Now, many times other than this distributed loading or concentrated loading, we get loading which are in the form of a concentrated moment. Let us say that we have a beam, let us say this is a cantilever beam which is fixed at this end. Now, at a particular point in the beam, this beam is subjected to a moment m at this point. Now, this will have effect, or there will be reactive forces generated because of this application of this moment, and this kind of loading we call as concentrated moment. So, in general a beam member supported on certain kinds of supports, as we have seen the different kinds of support, can be subjected to different kinds of loading, could be concentrated load, the linearly varying load, uniformly distributed load, or concentrated moment, either individually or combinations of these different kinds of loads. When this member is subjected to all these transverse loading in the plane of its of the member, we call this particular member as a beam member when they are subjected to these kinds of loading, the transverse loading. And consequently, we will look into finally our objective is to evaluate the stresses in this member, but before we really go into the evaluation of stresses, we will have to look into that how internal forces are generated in this member because of the transverse loading. Now, in the previous modules we have seen that when a bar element is subjected to an axial pull, how the stresses generate within the at the internal part of the body, or because of the twisting moment how the stresses are generated in the bar. Now, we will look into that when a beam element is subjected to this transverse loading, how the internal forces or the internal stresses are generated. Now, based on these discussions what we had, in fact, the first of the analysis or evaluation of the internal forces is to evaluate the reactive forces. Now, whenever a beam member is to be evaluated for the stresses, we will have to find out the internal forces. Now, for evaluating the internal forces, the first step is that we will have to evaluate what are the values of the support reactions or what are the value of the reactive forces. Now, this is how, say for example, this is a simply supported beam which is supported on a hinge support on one end and a roller support at the other, having a length L which we call as span. Now, is subjected to a uniformly distributed load over this part, say of intensity Q per unit length, and let us say this particular length is A. Now, concentrated load, vertical concentrated load is acting at a distance of B from here. Now, an inclined load, let us say at an angle of theta, is acting at a distance of C from here, and this gap could be D. So, now if we draw the free body diagram, that means if we remove these supports and draw the corresponding forces, the reactive forces, we will have one vertical reactive force, one horizontal reactive force for the hinge support, and if we call this end as A, this end as B, then this is, let us call this as R suffix A, this is horizontal force suffix A, and at this end we will have the vertical force only as horizontal movement is allowed. So, we will have this as R B. So, these are the three reactive forces R A, H A and R B which are to be evaluated from the equations of statics, and as you know, we have three equations of statics which are summation of vertical forces as 0, summation of horizontal forces in the beam is 0, and summation of moment at any point is equals to 0. So, if we employ these three equations, we can evaluate three unknown quantities, and as you can see readily that this particular member is acting at an angle of theta. So, it has components in the vertical and the horizontal direction, and this horizontal component of this force, since there are no other horizontal forces. So, if when we take summation of horizontal forces 0, so H A minus this, if we call as say this as P1, this as P2. So, the vertical component is P1 sin theta and the horizontal component is P1 cos theta. So, H A minus P1 cos theta, this is equals to 0, means the direction of H A is in the positive x direction and P1 cos theta is in the negative x direction. So, that is why this minus sign comes in. So, this gives us the value of H A. Likewise, we can take the help of other two equations to evaluate R A and R B. So, once we know the support reactions, then we can calculate the other internal forces as well as we desire. Now, let us look into that how do we compute the internal forces. Now, when this beam member is subjected to the transverse loading, it will be subjected to stresses, as we have seen in the past. For some kinds of loading in the bar, they are subjected to stresses. Now, our objective is to evaluate those stresses, but before we go into the evaluation of stresses, we need to know what are the internal forces that are acting. So, if we talk or discuss in terms of an example, let's take a beam which is subjected to a transverse loading. Let us say that we have a cantilever beam. Cantilever beam means it is fixed at one end and free at the other, and let us say it is subjected to a load P. Now, we are interested to find out the internal forces at a section which is at a distance of x from this support. Now, if we separate out this particular part which we call as a free body diagram, now this particular part is subjected to the load P. Now, this has to be in equilibrium with the internal stresses that is generated at this cross section. Now, since at this moment we are not in a position to evaluate the stresses, so what we need to know is that, as we have seen in the past, that when a bar is subjected to an axial pull, that the summation of stresses at a point over the cross section gives us a stress resultant. So, here also when this is subjected to the load, transverse load, there will be stresses in the cross section and there will be thereby the stress resultants, and let us call those stress resultants as the different kinds of forces will be existing here. They are the, let us call in this direction the axial force and the bending moment. There will be three quantities at this: the axial force, the vertical force, the force in the horizontal direction, force in the vertical direction, and a moment. Now, depending on the type of loading or the forces that the beam member will be subjected to, we will have these quantities. Now, here since we do not have any horizontal force component acting on this beam, clearly the horizontal reactive force will be 0. Now, when we get this vertical internal force or the stress resultant, we call this vertical stress resultant as the shearing force V. So, at any cross section we take in this beam member, we get some stress resultant which will hold this particular part of the body which is freed from the whole body in equilibrium under the action of the load, and those stress resultants which are acting in the vertical direction to equilibrate the vertical forces, we call those vertical forces as the shear forces, which are the internal stress resultant, and which will be acting in the horizontal x direction, we call those as axial force, and which will be a moment which will be resisting the effect of the transverse loading in terms of the bending, we call those as the bending moment. So, the stress resultants that will be acting at a section are the shear force V and the bending moment M. Now, here to have a proper sense of the sign, let us look into that. If we cut off this particular bar at a section which is at a distance of, let us say x1 from the left end, and if we take the free body part of this end which is fixed here. Now, here this is the positive x direction, this is the positive y direction. If you remember the coordinate axis system as we discussed earlier when we have evaluated the stresses. Now, this is the positive x direction along which we have taken normal stress, this is the positive y direction, and we had taken this as positive z direction. So, to match with this criteria, what we have done is our axial force on this particular section is positive on this, the shearing force is positive over here, and the moment which is a anticlockwise moment, the perpendicular to which is projecting out of the plane, we call them as the positive. So, when we take the other side, consequently the other part of the beam where we have the load, then the corresponding actions which will balance this, they are the shear force which is acting downwards, the axial force which is in the opposite direction, and the moment which was anticlockwise here, it will be clockwise here. So, if we just take an element out from this particular beam which is this, and if we look into that particular element, then the kinds of forces which we call as positive are, this is shear on the right face is going upward, on the left face is downward, the axial face on the right side is pointing towards positive x direction, and on this side on the negative x direction, and this is the moment which is anti-clockwise here and clockwise on this face. So, this we call as the positive sign convention, and reverse of these are the negative sign convention, and this is what is reflected over here. If we look into that, if we take out a small part from a beam element, say this is a small part. Now, on the right face we have positive shear which is acting on upward direction, this is the moment which is anticlockwise moment, this is the shear which is going down, this is on the other face, and this is the moment which is the on the other face. So, this is the positive actions and reverse of this is the negative actions. So, as we have seen that shear forces and the bending moments are the axial force are like axial forces in bars and internal torques in shafts are the resultants of stresses which are distributed over the cross section, and these quantities are known as the stress resultants. As I was explaining to you that when they are subjected to the transverse loading and when we are interested to evaluate the internal stresses, there will be if we take sections, there will be stress resultants, because at this moment since we are not in a position to evaluate the stresses directly, what we are dealing with is the resulting force that is acting in that cross section, and they are the forces in the vertical direction which we call as shear force, the force in the horizontal direction which we are calling as axial force which is acting in the along the axis of the bar, and the moment which is resisting these external loads in terms of the bending, we are calling those moments as the bending moments. So, we are interested in a beam to evaluate what is the value of such shear force and the bending moments because of the transverse load that the beam is subjected to for different kinds of supports. And once we can compute this shear force and the bending moment, then subsequently we can compute the values of the stresses in the bar or the beam. Now, having looked into this, let us look into some examples where we need to evaluate the reactive forces and consequently the shear force and the bending moment. Now, here it says that determine the reaction components of the beam which are caused by the applied loads as shown in the figure. Now, here the beam on one end it is supported on a hinge and on the other end it is supported on roller. So, this is a simply supported beam as we have designated. So, this is a simply supported beam, and if you look into the type of loading that it is subjected to, here it is subjected to a linearly varying load from 0 at this point to 2 Newton per millimeter at this point and to 0 over here, again it is varying linearly. So, what the length of this 600, 300, these are all in millimeters. So, what this particular length of 900 millimeter, from 0 it is going to 2 Newton per millimeter and again it is coming back to 0. And at this particular point it is subjected to a constant moment which is 150 Newton meter, which we have designated as a concentrated moment. Now, all we will have to do is that we will have to determine the reaction components for this beam. Now, first let us draw the free body diagram of this particular beam. So, this is the free body diagram of the beam, where if we look into that we have shown the reactive components. Now, for a hinged support we have a vertical reaction and a horizontal reaction. So, let us call this reactive force as R A and this as say H A, and here we have the vertical reactive force over the roller which is R B, and since in the horizontal direction it is allowed to move. So, there is no horizontal force component over there, we will have only the vertical component, and also since at these both the ends the beam is allowed to rotate. So, there is no need for having any moment to hold this rotation back, hence there are no reactive moments. So, the three unknown quantities, the reactive forces are H A, R A and R B. So, these are the three unknown quantities which are to be evaluated from the given loading and employing the equations of static. Now, as we know that summation of horizontal forces as equals to 0, summation of vertical forces is 0, summation of moment equals to 0. These are the three equations of our statical equilibrium. Now, if we employ summation of horizontal force equals to 0, then here since we do not have any horizontal loading in the beam, then it gives us that H A is equals to 0. Now, if we take the summation of vertical forces is equals to 0, then the vertical forces we have are the reactive forces R A plus the reactive force R B, and this is equals to, or let us say, since R A and R B they are pointing upwards. So, both are added, and then let us add the other quantities. Now, here we have the loads which are triangularly varying. Now, if we look into this particular part, here this is 0, this is 2 over a length of 300. So, the load is half into distance 300 times 2 Newton per millimeter. So, this is the load. Now, this particular load is pointing downward. Since this reactive load R A and R B are upwards, so this is with a minus sign. Then if we take this particular part of the triangular loading, then again this is half into distance 600 millimeter into 2 is the loading, and this loading again is directing downwards. So, this is negative. So, this is equals to 0. So, this gives us that R A plus R B, this is equals to, this 2 gets cancelled, this is 300 plus this 2 gets cancelled. So, this is 600. So, this is 900. So much of Newton. So, this is equation 1. Now, another equation we can generate from summation of moment equals to 0. Now, if we take the moment of all the forces with reference to this particular point, say point A, if we take moment about A, then what we get, let us say if we start from this end, the moment of R B is causing an anticlockwise moment. Let us call R B times the distance is 336, 6612, so 1500 millimeter. So, R B into 1500, which is anticlockwise. Then we have a concentrated moment which is also anticlockwise. So, this is plus 150 into 10 to the power 3, so much of Newton millimeter. Then we have these forces which will have moment with reference to A. Now, this moment the load is acting vertically downwards. So, this with reference to point A will cause a clockwise moment. Now, these two moments were anticlockwise moment, which we have considered as positive. So, contribution of this moment will be negative. Now, if we take this particular load which is half 300 times 2, which is 300, and 300 is acting at a point which is 1/3 from here. So, the distance from here is 2/3 of 300. So, the load is half into 2 into 300. So, 300. So, this is minus 300 times the distance is 2/3 of 300. So, into 2/3 of 300. So, that is the contribution of the moment from this part. The contribution of this particular loading, the loading is half of 600 times 2. So, this is again 600. So, again this is in a clockwise direction. So, minus. So, 600 into the distance is the action of this load is 1/3 from this end. Now, from here to here this is 600. So, this particular distance is 200 and the distance from here is 300. So, total distance of this load from this end is 500. So, this is into 500 and this is equals to 0. So, from this particular expression, if we compute the value of if we remove this particular part, wherein we have one equation that R A plus R B equals to 900 Newton, and second of equation gives that from R B equals to this equals to 0, gives us a value of R B as equals to 140 Newton. If you compute this, you will get the value of R B from this expression as 140 Newton. So, from equation 1, from R A plus R B equals to 900 gives us R A value as 900 minus R B, which is 140 Newton. So, this is equals to 760 Newton. So, this is the value of the reactive forces R A and R B, and H A equals to 0. So, the results are R A is equals to 760 Newton, RB is equals to 140 Newton and HA is equals to 0. So, these are the three reactive forces that we have. Now, let us look into another example problem wherein we will have to evaluate the reactive forces, the shear force B and bending moment M at C at this particular point, which is at a distance of 0.5 meter from point A. So, we will have to evaluate the shear force and bending moment at this point, and we will have to find out the reactive forces. Now, you can really recognize this particular beam. This particular beam is fixed at this end and free at the other, and as we have designated, this particular beam is known as cantilever beam. This beam is fixed at the one end and the free at the other, and it is subjected to what kinds of loading? It is subjected to uniformly distributed loading over a distance of 2 meters and a concentrated loading at a distance of 1 meter from support A. So, a cantilever beam subjected to this load, first you will have to find out the reactive forces, and secondly at this point, at this section, we will have to find out the shear force, the stress resultant, shear force B and bending moment M. So, let us look into these values. First, if we draw the free body diagram of this, then the free body diagram looks like this, that on this fixed support we have the reactive force, which let us call this as RA, the horizontal force which is HA, and the moment which is M or MA. Now, we will have to compute the reactive forces. Now, here since we do not have again horizontal forces, so HA is equals to 0. From summation of horizontal forces, it gives HA is equals to 0. Now, from summation of vertical forces, RA, which is vertically upward, other loads are being vertically downward. So, minus 4 minus 3 kilonewton per meter is the distributed load over a length of 2. So, 3 times 2, this is equals to 0. So, this gives us the value of RA as equals to 10 kilonewton. Now, if we take the moment of all the forces about this particular point A, now we have the support moment MA, which we will have to evaluate, and the 4 kilonewton force. Now, this moment which we have assumed here as anti-clockwise as positive. So, 4 kilonewton is contributing as a clockwise moment. So, MA minus 4 times 1 meter, so much of kilonewton meter, and this distributed load is 3 kilonewton per meter times 2 is 6 kilonewton, which is acting at the center of this length, which is at a distance of 1 meter. So, the distance from here is 3 meters. So, minus 4 times 1, and this is also in the clockwise direction. So, minus 6 into 1, 1 and 1, this is 3. So, MA gives us as equals to 22 kilonewton meter. So, these are the values of the reactive forces, that the vertical reaction is 10 kilonewton, horizontal reaction is 0, and the moment value is 22 kilonewton meter. So, these are the three values at this particular support. Now, what we need to do is that we need to compute the value of the bending moment and shear force at this particular point. Now, let us compute the values of the bending moment and the shear force at that particular end. Now, if we take the free body of the cantilever beam from the right hand side, so this is the free body diagram where we have the distributed load over the length of 2 meter, which is 3 kilonewton per meter. We have a concentrated load over here, which is 4 kilonewton. So, this distance is 2 meters, this distance is 1 meter, and we will have to find out the bending moment and shear force, which is at a distance of 0.5 meter from here. And here we have, since on the left hand side, so we have the positive values of shear as this and the bending moment as this, and since there are no horizontal forces, so we are ignoring the axial force. Now, if we take the summation of the vertical forces, then V plus 4 kilonewton plus 3 into 2 is the distributed loading. This gives us a value of V as equals to minus 10 kilonewton. So, the sign negative indicates that it is acting in the opposite direction as we have assumed. Now, if we take the moment of the forces about this particular point, let us call this point as C. So, moment C, now this is in the anticlockwise direction, 4 kilonewton also is causing a moment in the anticlockwise direction. So, plus 4 into 0.5, this load also is causing a moment in an anticlockwise direction. So, plus 3 into 2 into the distance is 1 plus 0.5, which is 2.5. So, this is equals to 0. This gives us a value of mc plus 2 plus this is 15, this is equals to 0. So, mc is equals to minus 17 kilonewton meter. So, the shear force which is acting at this particular cross section is 10 kilonewton, the bending moment which is acting at this cross section is equals to 17 kilonewton meter. In fact, we can achieve these results similarly if we take the free body of the other end, and we can here we have already computed the reactive forces. So, from this we can find out that what will be the values of the shear force and the bending moment, and they should be identical. So, we can take both the halves free body of either part and we can compute the values of the shear force and the bending moment at that particular location, and at any location if we like to find out, we can compute that. Well, we have another problem in which the beam ABCD has overhangs at each end and carries a uniform load of intensity Q. For what ratio B by L will the bending moment at the midpoint of the beam be 0? So, you look into this problem, try to solve it, next time we will discuss about it. And we have another problem in which you will have to determine the value of shear force and the bending moment at a point which is at a distance of 2 meter from here, and here a force which is acting at a distance of 1 meter from A will produce a moment over here. For this you will have to compute the values of the reactive forces and thereby the shear force and the bending moment. So, we will discuss this problem next time. Now, let us summarize then. In this particular lesson we have introduced the concept of beam, its type and different types of supports and loads that the beam member is subjected to. Then we have evaluated the shear force and the bending moment in beams. We have looked into some examples to evaluate the reactive forces, shear force and bending moment for different types of loading. Well, these are the questions set for you, that what is the difference between a bar and a beam, what are the different types of supports that are used in beams, and what is the sign convention for shear force, bending moment and axial force. Now, answers to these questions you will be able to know once you go through this particular lesson. Well, we will give you this answer in the next lesson. Thank you. Welcome to the second lesson of the fifth module, which is on bending of beams part 2. In fact, in the last lesson of this particular module, we have discussed some aspects of the bending of beams. We have introduced what is meant by beam, and then we have introduced the concept of shear force and bending moment. Now, in this particular lesson, we are going to look into the relationship of shear force and bending moment with the different types of loadings as we will go along. Well, then once this particular lesson is completed, if someone goes through this particular lesson, one should be able to understand the relationship between different types of loads and the stress resultants, which are shear force and bending moment. And if you remember